Yeah.
Good evening, sir.
Hello, sir.
Hi.
Good evening, Professor.
Okay, can we get started?
Yes,
Sure, sir.
Yeah. All right. So in yesterday's class, we have discussed the concept of crystal and a lattice, and we have seen the difference between crystal and a lattice. How do we identify a lattice? By identifying identical points and removing the background thing, right? So now in today's class, we will look at, okay, if the set of identical points in a geometry are identified, then that constitutes a lattice points, and then you will be you will be able to construct unit cells out of these lattice points. So now, what are the different kinds of these unit cells that are possible in a crystal structure? So this is something that is very fundamental that we need to understand, or it's a good information to have when you are participating in the discussion about various crystal structures. So in early as 1850s, this person called Breve has shown that all the crystals could be divided into only 14 unit cells. You will not have anything other than these 14 unit cells. Every crystal system will be one of these 14 unit cells. That means if you look at various crystal structures of materials that exist in this universe, they can only be one of these 14. It cannot be anything more or less, right? So we discussed already that the unit cell is the simplest repeating unit in a crystal. And we know that all parallelopipes, so all are valid unit cells, and in a given unit cell, opposite faces should be parallel. And the edge of the unit cell should be connecting equivalent points. What do we mean by an equivalent point? A lattice point, if you take two lattice points are identical, equivalent. That means the environment surrounding them is exactly the same, whether you sit on lattice point 1 or lattice point 2 or lattice point 1000, right? And we have also seen in yesterday's class that it is possible for us to have more than one unit cell for a given crystal structure. However, the convention suggests that you choose the smallest unit cell with highest level of symmetry. That is how you choose, you say that the crystal is having a such and such unit cell. Okay. So according to the Brevet's definition, so you have these 7 fundamental geometries, right? They are called the cubic crystal, tetragonal crystal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. And some variations of these 7 families will constitute total 14 Brevet lattices. What do you mean by a cubic crystal? A cubic crystal is characterized geometrically by having all the 3 sides equal, A equal to B equal to C, and all angles are 90 degrees. And if you start relaxing the constraints, that means you are relaxing the symmetry level. And as a result, you will have different structures. Okay. So, in summary, you get so these are the 14 types for each crystal family: cubic family, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. In that, you will have different variations. All these variations put together, you will have 14 Brevet lattices. For example, if you look at the cubic system, a cubic system can exist in a primitive lattice. What do you mean by primitive unit cell, by the way? What is a primitive unit cell?
It has only one.
Yes, it has only one
lattice point
per unit cell. Very good. So, as we have discussed, for a crystal structure, you can have a primitive unit cell or a non-primitive unit cell as well. So, if you look at the cubic crystal, you will see that the cubic crystal will be existing in the primitive unit cell structure, which is called simple cubic structure. You will have 8 corner atoms, and that's all. Atoms are sitting at 8 corner points. And you have another structure called body-centered structure and face-centered structure. Body-centered means you will have, in addition to these corner atoms, you will have one atom at the body center. And face-centered means each face center will have one atom. All these are cubic crystals, just that this is a primitive cubic crystal and this is face-centered cubic crystal. Okay. Now, you see that in a case of hexagonal, you have 2 cases, rhombohedral and hexagonal. You see that only primitive unit cells exist. The base-centered, body-centered, face-centered do not exist. It is not possible. Similarly, for tetragonal, only primitive and body-centered exist. Orthorhombic will have possibility for primitive, base-centered, meaning only there will be atoms at the 2 base, this base and that top. Because why? Normally base-centered means only at the base, right? But why is there an atom at the top and still we call base-centered?
It will be a base of next element.
Because that will be the base for the next unit cell here. Because you have to tile unit cells in all the directions. And monoclinic will have only base-centered, triclinic will have only primitive. Now the question is, why is that some crystals families have only a specific crystal possible, that means specific unit cell possible, others are not possible. For example, a base-centered cubic crystal is not available. Why is that? So, the same figure that I have shown, a cubic will have, all of them will have primitive. I means body-centered, F means face-centered, C means end center or base-centered. You see that cubic crystal have body-centered, face-centered and primitive, but it does not have end-centered unit cell. So now the question is, why is that a cubic crystal does not have an end-centered unit cell? let us try to look at that. If at all an end-centered cubic lattice exists, it should exist like this, isn't it? This is how an end-centered cubic lattice exists, unit cell exists. Now, let me tile this fellow with the next end-centered cubic lattice. Okay? If you tile these two guys, then you will see that you can actually construct another primitive unit cell. Here, this guy has only primitive unit cell, and if you tile this fellow, you will generate exactly the same structure. But instead of using a non-primitive unit cell, I could use a primitive unit cell to describe that, which means this primitive unit cell is same as this end-centered cubic crystal. And hence, end-centered cubic crystal is non-primitive, or hence it does not exist, and it can actually be seen as tetragonal, because primitive tetragonal is that, basically pulling it in one direction. Okay? These two sides are same, and this side is not same. A equal to B, but not equal to C. It doesn't appear that A equal to B because of the isometric view that we are looking at, but actually this is a diagonal, half diagonal, this is half diagonal. These two sides are same, this guy. If you take a cubic crystal and pull it in one direction, that becomes tetragonal. The moment you pull it in one direction, then you are actually disturbing the symmetry in one direction, right? If you take cubic crystal, if you rotate it about any one of the axes, all 90 degrees will give you same lattice points. Imagine a tetragonal one, that will not give same level of symmetry. So if you look at a cubic crystal, you will have three fourfold axes. The moment you pull the cubic crystal in one direction, you will destroy two fourfold axis symmetry. It will have only one fourfold axis, because in the other two directions it will be 180 degree, two-fold symmetry only. Fourfold symmetry in two axes is lost by pulling a cubic crystal in one direction. Is that clear? Are you able to see that? Why a tetragonal has only one fourfold axis? Cubic has three fourfold axes, that is along x direction, y direction, and z direction. If you rotate by 90 degrees, you will again reach the same lattice points. But if you take a tetragonal, you will not reach that same lattice point. Only when you rotate about one axis, you will reach other axes. About z axis, you will reach, but x and y axis, because you have expanded about z axis, that symmetry is lost. And similarly, orthorhombic will have three two-fold symmetry. Hexagonal has one six-fold symmetry. Rhombohedral had one three-fold symmetry. Monoclinic has one two-fold symmetry. Triclinic has no symmetry. That means no matter what you rotate, you will not reach the same points unless it is 360-degree rotation. Now, if you look at all these things, hexagon has the highest level of symmetry, six-fold symmetry, followed by cubic because it has three fourfold symmetries. Because it has six-fold symmetry, this is to be seen as highest symmetry level. Okay. All right. So that is just to describe what type of different unit cells that are possible. Now,
Sir, what is the meaning?
Yeah, please go ahead. Yeah.
What is the meaning of six-fold, four-fold?
So in the yesterday's class, so let me show this to you, maybe by drawing. 1 minute. Let me take 1 minute.
Threefold is XYZ.
Let me demonstrate that. Give me 1 minute. I will demonstrate that to you in.
Sir, am I audible?
Yes. Are you able to see my screen?
Yeah.
Yeah.
Sir, got
Okay. So here I have drawn a square, correct?
Yes, sir.
So now if you look at these points A, B, C, D are my lattice points. Okay.
Yeah.
If I am rotating this fellow by 90 degrees. Okay.
Yeah.
If I rotate this fellow by 90 degrees in the clockwise direction. So let us say if I am rotating this fellow by 45 degrees, how does it look like?
So maybe just to understand, every 60 degree, if it is rotating and there is a symmetry, then it is sixfold.
Absolutely. So every 90 degrees if I am rotating, after rotating these points about its axis, about the central axis, if these points again are occupied by the corners,
Yeah.
that means these corner points should be our lattice points, right?
Yeah,
For
yeah.
a
Yeah.
square, if I rotate it by 90 degrees, only then it will occupy these corner points. Otherwise, it does not, isn't it?
Yeah,
Yeah,
yeah.
sir, got it.
So 360 by 90 is 4-fold.
4.
Now, if you think about a cube, if you take about a cube, if you look at this is a cube, right? You can rotate about this axis
Yes.
and you can also rotate about this axis and you can rotate about that axis. In all these guys,
Yeah.
if you rotate by 90 degrees, you will occupy the same lattice points. Can you see that?
Yes.
Yeah.
So because you can rotate about 3 different axes, each axis is one axis. So like that you have 3 axes about which you can rotate with 4-fold symmetry. That is why it is called 3 4-fold symmetries.
Okay.
Now if you
Got it,
take
sir.
now if you take tetragonal, this fellow. If you take this fellow, only if you rotate it about z axis by 90 degrees, then you will retrace these points, isn't it? This, let us say this is my z axis, vertical line. Can
Yeah,
you see
yeah,
that?
correct.
Yes, sir.
But now let us look at rotating it
Yeah, yeah,
about
got it, sir.
rotating
Yeah, yeah,
about
yes.
this line. Yeah. Okay. So for hexagon, you just need to rotate by 60 degrees. It will get it will occupy the same points, but that happens only about one axis. That is why hexagon has 6-fold axis, one 6-fold symmetry. Okay.
Got it, sir.
Got it, sir.
Yeah.
Thank you.
All right.
Thank you.
Now let us look at the unit cell. Now we need to understand unit cell geometries. As we have said, in a unit cell, you have it's a 3-dimensional geometry that we are talking about. And let us say this is my x-axis, that is my y-axis, and that is my z-axis. Okay. And usually we will use right-handed coordinate system. And hence, once you define x and y-axis, the z-axis is fixed. And unit cell length, edge length along x-axis is usually described by a letter A. Along y-axis is described by letter B. Along z-axis is described by C. And the angle between x and y, y and z, z and x are represented by gamma, alpha, beta, or alpha, beta, gamma respectively. Okay. So these are the angles between the respective faces.
Sir, I have a question over here. Can
Yeah.
I ask, sir?
Yeah, please.
Sir, basically, with the previous concept that you have taught us just now, the fold axis actually. So the unit cell which has more, I would say, the like freedom of rotation and like acquiring the same lattice point, that will be more close packed crystal, I would say. Like, is implication of that will be like that only, or what? What I mean to say.
In some sense, yes, because that is a hexagonal will be more close packed.
So basically, sir, my question is, I'll put in this way that if we have more freedom of rotation, or I would say the fold axis that you have told. So what is the advantage in having it on the crystal? So
No,
what are
yeah,
the
so we will talk about it. Basically, one of the points that you're talking about is the close packing of planes and atoms is one of the aspects, and that will influence our mechanical properties. We will talk about it very soon. Okay.
Okay, noted, sir. Thank
Yeah.
you.
And so if you are talking about a cubic crystal, all that we are saying is A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. That is what we mean by a cubic crystal. That is geometric definition. But real definition is from the symmetry level. A cubic crystal is one which has 3 fourfold symmetries. That is how crystallographers define symmetry, a cubic crystal. They don't usually necessarily, this A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees is an outcome of that 3 fourfold axis symmetry. Okay. So any typical unit cell is designated by these parameters A, B, C and alpha, beta, gamma. Okay. So that is very important. So you take the origin of the coordinate system at one of the cell corners. You can decide where you want to take your origin. It need not be only here. You could take here or here or here. Accordingly, you define your the lattice parameters. So these A, B, C, alpha, beta, gamma are called lattice parameters. Okay.
Sir,
Yeah.
sir, just to clarify, this alpha is the angle between z axis and plane formed by AB.
Yes.
Okay, sir. Thank you.
Yeah. So, as we have discussed, we have already said it several times, unit cell is the basic building block of a crystal structure. It represents the symmetry of the crystal structure, and all the atom positions in the crystal may be generated by translation of the unit cell by integral multiple distances along its edges. What is the meaning of that? So, if you want to generate the next set of lattice points, so let us say this is one lattice point, each corner point is a lattice point. When you are translating the unit cell, you should translate by integer multiples. That means if you are translating this cube along x direction, you have to translate it by n times a, where n is a integer. You cannot translate it by a by 2 distance and say that, oh, it did not meet a lattice point. That is not how the translation works. The translation works by moving it by integer multiple times. So n times a, if you n equal to 1, it should reach the same kind of lattice points. N equal to 100 also, it should reach the same kind of lattice points.
Sir, is it because the lattice points are being shared?
Sorry?
So is it because the lattice points are being shared for each unit cell?
No, lattice points are shared, but not all lattice points are equally shared by unit cells. No, some lattice points are not shared. Adjacent lattices might share. For example, if you take a body-centered unit cell, that body-centered atom, or that is a lattice point, is not shared by other unit cells, isn't it?
Yes, sir.
The point is, when you are generating lattice points, if you look at the lattice points, you have to take a unit cell, which by translating that unit cell, you have to fill the entire space. That is the idea. But how do you translate it? So if I say that, yeah. So let us say that is my crystal lattice points. And let's say my unit cell is that. Okay. Now if I move this unit cell by the same amount, I will see my next lattice points. That means how much distance I have to move? Whatever is this length, in that direction I have to move by the same amount. Instead of moving that, if I move it here, are the corner points meeting the next lattice points or not?
No, sir.
No. So then I cannot say that what is the meaning of a unit cell when you take a unit cell, and if you translate that unit cell, you should be able to fill the space completely. But what is qualified to be a unit cell? A unit cell is a geometry in which all the corner points are occupied by lattice points. So the translation should be done in a specific manner. The translation should be done in a manner in which it is translated by integer multiples of the lattice length, right? So it should be 1 times. If you translate, you will reach these points. If you translate two times, you will reach these points. I have not drawn it perfectly, but that is what it means, right? If you translate it 3 times, again you will reach those lattice points. That is the meaning of filling the entire space by translation. Okay.
Yes, sir. Thank you.
Need to erase this fellow. So now let us try to understand how do we describe a crystallographic point. When I say crystallographic point, we are talking about any position in the crystal. Typically, when we are talking about crystallographic point, we actually talk about a lattice point in the crystal. Okay. So that means a point where an atom is sitting in some sense. So the position of any point within a unit cell, is specified in terms of its coordinates. So for example, if you take this unit cell, along x, the length is A, along y, the length is B, and along z, the length is C. You can see that along x length is A, along y length is B, along z length is C. Okay. Now when you are talking about description of a point, what you will do is you will describe the position as fractional multiples of that unit cell. What do I mean by that? Suppose if I am talking about this point P, this point P is identified by Q times A along x direction, R times B along y direction, S times C along z direction. That is how you will reach point P. Then, in order to describe that crystallographic point in crystallographic language, the way to describe that is not to write the absolute distances, but mention it as fractional multiples. So that means you simply write Q, R, and S. And you don't put commas besides them. You just simply write those 3 numbers. So for example, in this particular picture that I have shown, Q is equal to 1 by 2, R is equal to 1 by 2, S is equal to 1 by 2. Do you agree? Because 1/2 of A, 1/2 of B, 1/2 of C. So the representation of this point P will be 1 by 2, 1 by 2, 1 by 2. That's how it should be represented. Right? That is the way a crystallographic point should be represented within a unit cell. Is there any question there?
So that is like saying we set the origin to one corner of the unit cell.
Exactly. That's what I said. No, you can choose origin to be anywhere you wish. And accordingly, you define the distances. So now, let us say you have chosen your origin here instead of here. Okay. If you are choosing your origin here, then you have to move along negative x-axis, isn't it? Yes or no?
Yeah.
Then it will be minus 1 by 2. Okay.
Yes, I got it.
Yeah. So now let us look at, let us say you have this crystallographic, this unit cell whose length along x-axis is 0.48, A is 0.48, B is 0.56, C is 0.5 nanometers. Now you need to locate the point 1 by 4, 1, 1 by 2. So how do you identify that point? The x projection is 1 by 4. So along x, it is at what distance? 1 by 4 times 0.48. Isn't it? Along y, 1 times 0.56. Along z, 1 by 2 times 0.5. So if you look at this fellow, if you have to locate 1 by 4, 1/4 along that guy, and then along y, 1 full length, and along z, here 50%, 1 by 2. And that will be your crystallographic point, right? So x is equal to 0.12, 0.56, 0.25, and 1 by 4, 1, and 1 by 2. And that is your crystallographic point. That is the point that we are referring to. Okay. Is there a question here? Everyone understood this point? How to identify a crystallographic point given its indices? These are called crystallographic point indices. Now, I'll give you one exercise. This is a body-centered cubic structure. And I'm mentioning, because it is cubic, it is A. Now I would like you to write the crystallographic point representation for all these 9 atoms. 8 corner atoms and 1 center atom. Can you please write down?
So I can assume the origin at 1, na? Right? Hello? Hello, sir?
Yeah, Roshan, you can assume.
Yeah. So now, what will be the crystallographic point representation for point 1?
I assume it's 0, 0, 0.
Yeah, it should be 0, 0, 0. Why should we assume it to be 0, 0, 0?
Because you told us like origin can be anywhere. Suppose
But
you
I have
find,
given the origin, no? I have given the
sorry.
origin.
Sorry, so I just missed that point. Sorry.
Yeah. How about point 2?
1,
1, 0, 0.
1, 0, 0. And point 3?
1, 1, 0.
Point 4?
0, 1, 0.
0, 1, 0. Point 5?
1 by 2, 1 by 2, and 1 by 2.
Yeah.
It's
You should not
assuming it's
write.
center.
You should not write 0.5, 0.5, 0.5. You should write 1 by 2, 1 by 2, 1 by 2.
Right, sir.
Okay? Yeah. Point 6?
It's basically 0, 1, 0.
0?
1, 0.
0, 0, 1.
So 0, 0, 1. Sorry.
0,
0,
0,
1.
7?
7 will be 1, 1, 0, 1.
1, 0, 1. 8?
Yeah. 1, 1, 1.
9?
That will be like 1, 1,
0, 1, 1.
0, 1,
0,
1.
1,
sorry.
1.
Yeah.
Very good. Okay.
Yeah.
So it's pretty simple, no? We know how to identify crystallographic points. Now, for the same thing, imagine your origin is at 5. So that means the x-axis, sorry, the coordinate system is moved to 0.5. Then can you write the crystallographic points for all of them? Just your coordinate system has moved from 1 to 5 without rotation. It is just translated there.
So point 1 will be minus 1 by 2. Then again minus 1 by 2, and then again minus 1 by 2, in my opinion.
We have to subtract 1 by 2 from each and every point of this matrix.
You have to subtract 1 by 2.
Yes, sir. That's a valid thing. Yeah.
Okay. All right. So you will be able to figure that out. Good. So similarly for FCC, you know what is an FCC, right? How does an FCC look like?
face-centered cubic.
Yeah. So in an FCC, you will have 5 will not be there. So let us say 1, 2, 3, 4, 9 may be 5. We'll make 9 as 5, 5, 6, 7, 8. They will not change. And 9 is on this face, 10 is on this face. Can you tell me what are the coordinates of 9 and 10?
One by two,
one by
one,
two.
1 by 2.
1 by 2,
1 by 2.
1 by 2, 1 by 2. Very good. We have done that just a while ago. All right. So good. So we know how to identify crystallographic points. Once you have these fractional values, you just have to write them side by side. That is as simple as representing a crystallographic point. And
Sir,
next,
one question, sir. I'm sorry to just
please,
bother you a bit.
Please.
Sir, 5, we told that 1 by 2, 1 by 2, 1 by 2. Okay. And you told that you should not write 0.5, 0.5, 0.5. So like, I got, like, personally, I got the logic, but I just wanted to get confirmed why it is so.
That is, so there is no logic here. It is only a universal representation system that crystallographers agreed to.
Oh, okay, sir.
Okay.
Okay, sir.
Yeah,
Noted.
that's all.
Noted.
Yeah. And now next we
sir.
will talk. Yeah, please. Yeah.
Actually, here A value is not given actually. So are we assuming it to be 1 actually?
No, you are not assuming it to be 1 because whatever may be the A value, if you go previously, no, if I see the first picture, it is written as fractional multiple of that distance. So we are writing only Q. We are not writing Q times A here.
Okay.
Yeah. So this is a fractional multiple. Yeah.
Okay.
Yeah. So next we will talk about crystallographic directions. What is a direction means? It's a line. It's basically a line between 2 points. Or in other words, we are talking about a vector, representation of a vector. Now, how do we determine the directional indices? So there is a procedure that one needs to follow in order to be able to represent the vectors in consistent manner. What we need to do is, whenever you want to represent a vector, the vector should be positioned to pass through the origin. Meaning, if at all the direction vector is not passing through the origin, you are allowed to translate the vector without rotating it. You can translate the vector so that the vector's tail is passing through the origin. So that is the first thing that one needs to do. Then, once it passes through the origin, once the tail is attached to the origin by translating it, then what you need to do is, you need to find the length of the projections of these vectors on each of the coordinate axes. Projection onto x-axis is A, projection onto y-axis is B, and projection onto z-axis is C. And then you need to take these 3 numbers. These projections need not be integers, right? Integer projections. They could be fractional projections. All that you need to do is, you need to multiply these 3 numbers A, B, C with a common factor so that all 3 numbers are reduced to smallest possible integer. All 3 of them should be multiplied with the same factor so that there are no fractions there. Everything is an integer. Okay. And then once you have those integers, call them U, V, and W. And again, without putting commas, you write U, V, W, but enclose them with a square bracket. So when you are looking at crystallography, and if someone represents something as 1, 2, 3 in square brackets. That means they are referring to a crystallographic direction 1, 2, 3. Okay. So now let us look at it. This we will understand by doing it. Let us look at it. So let us look at this fellow. Let us try to understand crystallographic representation for this direction vector. Okay, this crystallographic direction. Now,
Guys,
Hi.
Some disconnect happened, sir. Sir, you are in mute, sir. Sir, you are on mute.
I'm sorry, I think I got disconnected, right?
Yes, sir.
Yes, sir.
Are you able
screen
to
is
see
with
it? Now you are able to
Yeah,
see
yeah.
the screen?
Yes, sir. Yes, sir.
Yes, sir.
Where did you lost me? When did you lost?
The next slide only.
Okay.
Next slide.
So the crystallographic direction, when you want to construct, the way to construct is the following. Okay. So you have a right-handed XYZ coordinate system, and that should be first constructed. For convenience, the origin may be located at a unit cell corner. You choose your origin to be at a unit cell corner. Okay. And let's say that the coordinates of 2 points that lie on the direction vector, for example, the tail is x1, y1, z1, and the head is x2, y2, z2. Then you simply replace x2 minus x1. So you subtract tail points, head points from tail points. This is regularly that we do. And the coordinate differences are normalized in terms of the lattice dimensions. Lattice dimension A, B, C. And that will give you 3 numbers. And these 3 numbers are multiplied or divided by a common factor to reduce them to smallest integers. So that common factor could be n. This is how you could do. Okay. So let us look at this fellow. This is your direction, crystallographic direction. So one way to go about it, all that we need to do what? It is cutting x1 axis, x-axis at A. So x1 is equal to A, y1 equal to 0 because it is not cutting, it is here, and z1 is equal to 0. So that is what it is, and this is x2, right? You identify the position point locations of x2, y2, z. So that basically means that you are trying to find out the crystallographic point coordinates and for the head and tail. And as per the prescription, you find the difference between x2 minus x1, y2 minus y1, z2 minus z1, and divide that with corresponding corresponding lattice parameters A, B, and C. Right? Then you got x2 minus x1 by A, y2 minus y1 by B, z2 minus z1 by C. x2 minus x1 is what? Minus A. Right? x2 minus x1 is minus A. y2 minus y1 is B, z2 minus z1 is C by 2. So now you don't have it in terms of A, B, and C, but a fraction of C. So one half times C is what is there. Now what you need to do? So this you divide it with A, B, and C, then you will get x2 minus x1 is minus 1, plus 1, and 1 by 2. That is what you have. Since you have minus 1 and plus 1 and 1 by 2, what is the common factor that you can multiply in order to convert that into set of integers. The common factor to be multiplied with is 2. So when you do that, minus 1 times 2 is minus 2. 2 times 1 times 2 is 2. 1 by 2 times 2 is 1. Then you got these three are your indices called minus 2, plus 2 and 1. In crystallography, we don't write minus 2. If it is minus 2, we represent it as 2 bar. When you say a bar above it, then it's a negative number. 2 bar, 2 and 1. And these two guys written side by side and enclosed in square brackets. And that is how the representation of this fellow, this particular crystallographic direction can be done. Is that clear?
So why do we choose 2 over here?
Yeah. So let me write down. Okay. So x2, after doing this, what did we say? After finding these differences, I need to divide those differences with corresponding lattice parameter, right? So x2 minus x1 divided by, that is minus a. Minus a divided by a is how much?
-1.
Minus 1. So that is minus 1. And b divided by b is plus 1.
1 by 2.
c by 2 by c is 1 by 2. Correct?
Yes, sir.
Do you agree with that? Now, if these resulting numbers are not integers, then what you need to do is you need to multiply all of them with a common number. That is a crystallographic procedure to represent directions. So what is the common number that you will multiply with in order to make it smallest integer?
2, sir. Getting it now.
Yeah. So if you multiply with 2, this becomes minus 2 plus 2 and 1. So since minus 2 should be written as 2 bar, that is why it is written as 2 bar. Since it is a crystallographic direction, it should be enclosed between square brackets. Is that clear?
Yes, sir. Yes, sir.
Yeah. So now let us draw 1, 0, 0 direction. How will 1, 0, 0 look like? What does it mean?
X-axis.
Yeah. So it is projection onto x-axis is 1, 0 projection onto y-axis, 0 projection on z-axis. That means it is not cutting z-axis or y-axis. That is your 1, 0, 0. Right? What is 1, 1, 0?
In XY plane diagonal
That
line.
is your 1, 1, 0. What is 1, 1, 1?
Diagonally in
Diagonal,
three
diagonal
directions.
also.
That is what we call body diagonal. Okay? Is that clear?
Yes, sir.
Now, how do we identify the crystallographic direction indices for this particular direction? How do we do that?
1, 2, 1.
1. So let us go in steps, right? So what is the projection of this fellow onto x-axis?
1 by 2.
Yeah, write down 1 by 2. Onto y-axis?
1.
1.
1. On z-axis?
0.
0. 1 by 2, 1, 0. Now in order to make it an integer, smallest possible integer, what should I multiply it with?
2.
2. So it should be 1 by 2, 1, 0 should become what?
1, 2, 0.
1, 2, 0.
1, 2, 0.
So instead of writing a by 2, because it will be anyway divided by a, so I am writing 1 by 2, 1, 0, 1, 2, 0. That is how you write these crystallographic directions. Now let us draw 1 bar 0 in a cubic unit cell. That again, I think I got disconnected. I don't know why the internet connection is very buggy today. Let's get restarted. So this is the figure that we are, right? This we have done, isn't it?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
Now let us draw this figure. So now if you look at this fellow, 1 is here, and now 1 bar means should I move left or right?
It should be left, sir.
Left.
Basically,
Left. Out of
left. Out of the cubic cell, actually, it's coming.
Yeah. So what I can do is I can actually stack another cubic cell to the left of it because this is chosen as origin, right?
Hmm.
Or I can actually move this entire thing here. My origin could be here. This
Yeah,
could be my
that's-
X, that could be my Y, that could be my Z. If that is the case, then 1 bar is this. This is the point. So my direction will be that, isn't it? I could actually put that because this is in the negative direction, or let me show you how the other thing can be done. Now when I stack it, now you can see 1 bar 0. Now the origin is here, then that is how it is. Imagine this origin moving here. Isn't it exactly same as this? Hello?
Yes.
Yes, sir.
Yes, sir. Yes,
There
sir.
is.
Yes, yes.
Yeah. So that is what we can do either way. Either way is fine. Both of them are acceptable. Okay. Okay. So for crystal structures, whenever we are talking about crystal structures, several non-parallel directions with different indices are equivalent. What do I mean by that? Let us take the case of cubic crystal. Okay.
Sir, I have a question over here.
Yes.
Can I ask?
Yes.
So
Yes.
basically, sir, we are having a very established, like what I'm going to say is vector coordinate system in the physics.
Mm.
Why can't we apply that and get rid of this type of notations? What are advantage we are getting by doing this?
Because when we actually look at X-ray crystallography indices, then it becomes much easier to identify some equivalent directions. I will talk about right now. This kind of a notation will be useful. It is exactly the same as your vector notation, but there is some procedure which allows us to see something called an equivalent direction, which I will discuss in a moment. Okay.
Thank you, sir. Thank you so much.
Yeah. So now let us look at the scenario. Now you have in this particular place, you have one atom, correct? Another atom. Oh, you are not able to see what's going on.
Visible, sir. Visible.
Visible, no? No, I'm drawing some atoms. Are you able to see the atoms?
Yes, sir. Yes, sir. Yes, sir.
Let us say this is a simple cubic system. Okay. Forget about everything else. So there are 8 atoms. Now, let me look at 2 directions. let me draw one direction, that is 1, 0, 0. Correct? And now let me draw another direction, that is, this is what 0, 1, 0. Do you agree?
Yes.
And that is 0, 0, 1, isn't it? Now I have 1, 0, 0, 0, 1, 0, 0, 0, 1. Are these parallel directions?
No.
No, they are not parallel. Good. Now let me also draw another direction. What is that direction?
1, 1, 1.
No, that is this guy extended out into the paper.
1 bar 0, 0.
1 bar 0, 0, right? And what is that fellow?
0,
0, 1 bar 2.
0, 0, 1 bar.
0, 0, 1 bar. Now, the interesting thing about these, let us look at only the positive directions, 1, 0, 0, 0, 1, 0, 0, 0, 1. The interesting thing about these things is these three are non-parallel directions. They are not parallel to each other. But if you are here, if you are moving in this direction by units A units, and you will reach the next lattice point. As far as crystal lattice are concerned, is there any difference between this lattice point and that lattice point?
No, sir, it should be identical actually.
They are
It should be
identical.
identical. Yeah,
So
yeah.
is there any difference between this lattice point and that lattice point? No, right? All 8 lattice points are equivalent. So if you take 1, 0, 0 direction in a cubic crystal, if I move A units, I am reaching exactly same environment. Either I move in 1, 0, 0 direction, 0, 1, 0 direction, 0, 0, 1 direction, or 1 bar 0, 0 direction, 0, 1 bar 0 direction, 0, 0, 1 bar direction. Although all these directions are non-parallel, they are all considered equivalent directions, because by traveling that much amount, equal amounts of distance in that direction, I am experiencing exactly the same environment. The neighborhood is exactly the same. And hence they are called equivalent directions. So, in other words, if I am moving along this direction, let us say I am experiencing some force field. Imagine yourself sitting on one of the atoms in the crystal, cubic crystal, and you moving along this direction, and you moving along this direction. If you are not having any sense of the directions itself when you are sitting in the crystallographic system, then what you will observe is that the force field that you experience while you are moving from this point to this point or this point to this point will be exactly the same. Because it is exactly the same, that means you are experiencing same environment throughout these directions, irrespective of in which direction you are moving. These directions are called equivalent directions. Is that clear? So, in crystallography, several non-parallel directions with different indices are equivalent. That means 1, 0, 0, 0, 1, 0, 0, 0, 1, 1 bar 0, 0, 0, 1 bar 0, 0, 0, 1 bar. For cubic crystals, these guys are identical. For non-cubic crystals also, they may be identical, but several non-parallel directions could be identical. So such directions are called equivalent directions. So if you have a family, particularly for cubic crystals, if you have a family of directions which are equivalent, then this entire family is grouped as a crystallographic direction family. So now if you look at these guys, all these 6 guys are obtained by permutations of 1, 0, 0. In all these directions, you will have 2 zeros and 1, 1. 1, 1 or 1 minus 1. Doesn't matter. But you will only have permutations of these 3 indices. And all of them are equivalent. That happens only for cubic crystals. For tetragonal, it will not happen. Because if you are taking a tetragonal crystal, only along the base 1, 0, 0 and 0, 1, 0 will be identical. But 1, 0, 0, 1 will not be identical because it is stretched. So you have to go farther. Then hence, that is not identical to, equivalent to 1, 0, 0 and 0, 1, 0 in a tetragonal structure. But for cubic crystal, it turns out that all permutations of these indices will form a family of equivalent directions, right? And if you are representing a family of directions, they are represented in these less than, greater than symbols. And then if you see something like that, then that means you are actually referring to a family of crystallographic directions, if you are seeing something like this. Okay? So they are equivalent irrespective of the order in which they appear. So 0, 1, 0, 1, 0, 0, 0, 0, 1, they are all equivalent. So for cubic crystals, you can take it without even thinking about it. What do I mean by that? If I say direction 1, 2, 3, direction 1, 2, 3 in a cubic crystal is equivalent to 2 bar 1, 3 or 2, 3, 1, 2, 1, 3 and so on. That is true for cubic crystal. Which means when you move along this direction or this direction, you will move by the same amount in order to reach the next crystallographic point, or the environment around you, the force fields around you, when you are moving along that path will be identical. That is why they are called equivalent directions. Okay? Any questions there?
Sir, can we just what I mean to say, by pictorial view, can we just have this clarity about this 1, 1, 2, 3 is equivalent to 2, 3, 2
Yes.
bar 1,
Yeah,
3 bar?
we can. So let me.
Yes, sir. I'm sorry, sir. It's bothering.
No. Please ask. I want you to ask me questions. That is the best way to learn this course. So let me see if I can share my iPad, because that's much easier. Yeah, you're able to see my screen?
Yes, sir. Yes, sir.
iPad. Yeah. So let us look at some simple systems. Right, let us say 1, 2, 3, 4, 5, 6, 7, 8. So let us say this is our x-axis, that is our y-axis, and that is our z-axis. Okay. Now let us try to identify the direction 1, 1, 0. What is 1, 1, 0? Projection onto x-axis is 1, y-axis is 1. So that is my 1, 1, 0. Do you agree? Yeah?
Yes, sir.
Now let us look at 0, 1, 1. it is on the plane 3, 4, 5, 6, right? Isn't it?
Yeah, that's right.
Because it is a cubic crystal, if I plot 3, 4, 5, 6, I am plotting 3, 4, 5, 6. That is my 3, 4, 5, 6, and that is my 0, 1, 1, right? And 1, 2, 3, 4 again. If I am looking from top view, one, 2, 3, 4. That is my 1, 1, 0. Correct? And we know at each and every corner, you have identical atoms. Isn't it? Now, if you look at 1, 1, 0 and if you look at this 1, 1, 0 line and 0, 1, 1 line, right? You see that you will feel exactly the same environment if I don't tell you that you are running on this plane or that plane. Because you are going to feel exactly the same environment by moving the same amount of distance, you will find the next neighbor. While you are moving, you will see your neighbor exactly at the same distance to your left and to your right, to your left and to your right. That is why these two directions are called equivalent. Is that clear?
Understood, sir. Understood.
Yeah. So
Got
now,
it. Yep.
not only that, if you look at this fellow, interestingly, you take this fellow. What are the direction indices of this? What will be the direction index of index of that?
0. First thing is 0, and second will be
First thing will
projection on
be 0 because it is intersecting x-axis at 1.
1
One.
bar.
0.
1 bar 0.
yeah, yeah.
Again, that will also feel exactly the same environment or not? Will it experience the same environment while you are moving from 3 to 1 or from 4 to 2?
Yeah,
It will be
it's
So,
it will be
as
same,
a
sir.
result,
Right.
all these guys are called equivalent directions. Similarly, if you have to plot 1, 2, 3, how would you plot 1, 2, 3? Let us say one of you have asked, how do I see 1, 2, 3 direction, right? So I got 1, 2, 3 direction. How would I have got? There are two ways to do that. First, divide this with largest number. Then this will be 1 by 3, 2 by 3, 1.
Hello.
Yeah.
Hello.
Or I can tell like this also, sir, that I have a point where projection on x is 1, projection
Yes.
on y is 2, and projection on z is 3.
That is correct.
Right.
But then you will go out of the unit cell.
That's right.
But
Yeah.
we are writing
Yeah.
crystallographic directions within the unit cell.
Right. Got it, sir.
That
got
is
it.
why I
Got
am doing this.
it.
Yeah.
Noted.
So now all that I need to do is I need to project 1 by 3 on x-axis. Let us say that is my x-axis projection. 2/3 on y-axis. So that means and z-axis. So that would be my 1, 2, 3, right? Because 2/3 and then 1. That will be my 1, 2, 3 director. So 2 bar, 1, 3 bar, all the combinations will be equivalent directions. Okay?
Small question, sir.
Yes, please.
In the 1, 2, 3, you divided by actually 3, right? Can I divide by 6?
You divided by 6. Let us see. Okay. So your question is why naturally you are dividing by 3. Let's go by that. 1 by 6, 2 by 6, 3 by 6. That will be 1 by 6, 1 by 3, 1 by 2. Right?
Okay. I got it.
Yeah.
It doesn't become an
It
integral.
doesn't matter because what you are doing is you are multiplying the vector with a scalar.
Yeah.
So it is, you are basically, see here we are not interested in the magnitude of the vector. We are interested in the direction of the vector. And hence it really does not matter whether you take it larger or smaller. All that we are trying to do is to represent the vector within the unit cell. Okay?
Clear.
Okay, good. So let me move on. So now let us look at you are seeing now slides, right? On your screen, are you seeing slides or are you seeing a notepad?
Notepad.
iPad.
iPad,
You're
sir.
still seeing the iPad?
Yeah.
Okay. Oh, yeah. I think I need to see what you are saying. Yeah. Sorry. Yeah. Now you are seeing the screen, I suppose, right?
Yes, sir. The screen is visible now.
Good. So now let us look at crystallographic directions in HCP, hexagonally close packed structures. So just now what we have learned is that all equivalent directions will have permutations of the symbols. So you just take, if you know one direction, you can always find all the equivalent directions and all of them will be put together. Only one in 3 set of indices you have to use and put them under Macaulay brackets, and then you will have that as your family of crystallographic directions. Now let us look at the crystallographic direction representation in hexagonal close packed structures. The reason why we would do that is because we deal with hexagonal structures in materials quite often. If you look at this fellow, you will have basis vectors A1, A2, and Z. 3 basis vectors, right? Like the crystallographic axis that we have. So that is your typical hexagonal unit cell. But when it is rotated and placed, then you will have this hexagon looking like unit cell. So in that, if you look at this direction, 0, 1 bar 0. Do you agree? And this is 1 bar 0, 0, which is an equivalent direction. So if you look at this guy carefully, here to here you have 0, 1 bar 0. Here to here 1 bar 0, 0. Here to here, what is it? 1, 1, 0. Can you see that? But according to the previous discussion, on this hexagonal plane, when you are moving from here to here, you will feel some force field. You will feel exactly the same force field when you are moving from here to here. That means this direction should be equivalent to this direction, isn't it? Or this direction. If it is an equivalent direction, then the indices should only be permutations of this. That means it should be some permutation of 1, 0, 0. It cannot be a new index if it is a equivalent direction. So if you are using this 3 index notation in a hexagonal crystal structure, your convention that the crystallographic direction, equivalent crystallographic directions will have same set of indices will be broken. Right? That is what we have seen here. So how do we circumvent this problem? So people have come up with some suggestions in circumventing this problem. So in this case, no permutations is possible for equivalent directions. So in order to avoid this, people have come up with something called a 4-index notation. Instead of 3-index notation, people have come up with 4-index notation, where you decide you have 4 basis vectors, A1, A2, and A3. Each of them are rotated about 120 degrees angle between them. Okay. A1, A2, A3 are in one plane and Z is perpendicular to that. And then you have 4 indices. Instead of UVW, you will have UVTW. And first 3 digits are projections along A1, A2, and A3. And the fourth one is projection along Z axis. Okay. Now, how does it work? If you have a 3-index notation called U dash, V dash, W dash, like 110, like we have seen, that can be converted to a 4-index notation using this formula. Let us not worry about how this formula is derived. But if you use this convention, then you will see that all crystallographic directions, equivalent directions, will have same set of indices, which are permutation. So the direction 110 that we have represented earlier with 3-index notation will now be represented as 112 bar 3. Okay. So how do we do that? Let us look at it. In order to do that, all that you need to do is reduced scale coordinate axis system may be helpful in identifying crystallographic directions in HCP. What do I mean by that? So the basal plane, this is what we call basal plane, the bottom hexagon base. That plane is called basal plane. It is discretized in such a way that every intersection of 2 axes is trisected by the other axis. So that means if you have 2 axes and you will have trisection of the other axis. So that means you can, which basically means this axis is trisected by this axis and similarly. So you are doing this kind of a grid. And along the Z axis also you have 1/3, 2/3 and 1. M is at 1/3, N is at 2/3 and this point is at 1. So now if I move along A1, 1/3 will be 1, 2/3 will be 2, 3/3 will be 3. That is how we represent the coordinates. Okay. Now, if I have to take 111 direction into hexagonal 4-index notation using the formula that I have given, if it is 111, then that becomes 1/3, 1/3, 2/3 bar and 1. That is what it becomes. So if I say 1/3, I have to move by 1/3. Another 1/3 means, so 1/3, next is plus 1/3 means this, right? So let us look at this. That is our 3-index notation. 1, 1, 1 will be this point. Now in the 4-index notation, I have 1, 1, 2 bar 3, right? Because I have to multiply with 3 now, because I cannot have fractions. So I have to multiply with 3, that this becomes 1, 1, 2 bar and 3. 1, 1, 2 bar 3. So let me see how that can be drawn. 1, 1, 1 in 3-index notation is 1, 1 and 1. So that is the point. Next I have 1, 1, 2 bar 3. So 1 along A1, along A2, 1, 1/3, along A3, 2 bar, meaning what? Negative 2. A3 positive is in this direction. So negative 2 means 1, 2. And then 3. 3 is 1 by 1/3, 2/3, and 3. 3 steps. So each step is 1/3. That's what it means. So 1, 1, 1, and then 4 index notation. 1, 1, 2 units minus direction, negative direction, and 3 units positive. So I reached the same point. So the 3 index notation 1, 1, 1 is represented by 1, 1, 2 bar 3 in a 4 index notation. Why we need this 4 index notation? So that all equivalent directions, now 1, 1, 2, 3 and 1, 2, 1, 3. So let us look at 1, 2, 1, 3. What is 1, 2, 1, 3? 1, 2, 1 means here, and then 3, and you will have here. So this direction and that direction are equivalent. That's what it means. Okay. That is 1, 1, 2 bar 3. Any questions there? In the hexagonal?
So it's
Sir,
quite,
no,
we have got the intent of the logic behind this 3 index and 4 index notation. But the point is that why we require 4 index notation? Like
No,
what
we,
is?
we don't need it. We don't need it. You can still live with 3 index notation. But when we are dealing with math, all that you wanted to see is that all equivalent directions are represented by same set of indices. Okay. So as you have seen earlier, we know 1 bar 0, 0, 0, 1 bar 0, 1, 1, 0. All three of them are equivalent or not?
Yes, equivalent. It's
They are
equivalent.
equivalent, but
Yeah.
they are not represented by same set of indices. You have 1, 1 and 2 zeros. Here also you have 1, 1 and 2 zeros. So these two can be simply seen as equivalent directions. But this guy, although it is equivalent, it does not have 1, 1 and 2 zeros, but it has 2 ones and 1 zero, which is a little inconvenient in terms of working with these directions. So in order to avoid that confusion, for the crystallographer's language, then people said that, okay, for hexagonal system, when you are dealing with, you use a 4 index notation that will allow you to have the same set of indices when you are representing a equivalent direction. So let us now look at in this particular scenario. Okay. What is this direction now called in the 4 index notation?
Minus
From
3,
here to
minus
here?
a 3, minus a 3, I would say.
So that is 0, 0, 1 bar 0, correct?
Yeah, yeah, yeah.
What is this direction? Zero, 1 bar, 0, 0. Isn't it? You are moving along, you are not moving along A1, you are just moving along A2. So
Yeah.
that will be 0, 1 bar, A3 direction you are not moving, so 0, and Z direction is also 0. And similarly, if you look at this fellow, what is the representation? 1 bar, 0, 0, 0. So all these directions are represented by 3 zeros and 1, 1. That is why they are all equivalent directions. Then whenever you say in equivalent directions, then you simply say 1, 0, 0, 0 in the angle brackets will represent family of equivalent crystallographic directions in a hexagonal system. Otherwise, you cannot represent that as a family because some of them are not. Okay. Because for example, 110 in 3 index notation is equivalent to 100 in 3 index notation for hexagonal system. In order to avoid that ambiguity, people have introduced this. However, if you are familiar, if you are aware of what is happening, you can still work with the 3 index notation. There is nothing that stops us. Okay.
Thank you, sir.
Yeah. And then you have represented points, you have represented directions. Now the most important, or not the most important, but next. So you have gone from 0th dimension, 1 dimension, now you have to go to 2 dimensions called planes. So how do we go about representing a plane? And the representation of plane is little bit more involved than points and directions. So I think we will discuss the representation of crystallographic planes in the next class, because we only got 4 minutes. I don't think we'll be able to cover that within that period. It needs at least 10 to 15 minutes to discuss that. Okay, so in that case, we'll discuss about crystallographic planes in the next class. Is that fine?
Yes, sir.
Yes, sir.
One query. Am I audible?
Yes, you are.
Sir, this crystallographic directions and the indices, based on the examples that you have shown, which is basically cubic and HCP, I'm understanding it will not be possible in triclinic. Am I right?
No,
Because
what
there
is
is no
not possible in triclinic?
In terms of writing it as a family notation, like
So family notation, what happens is, in a triclinic system, you will not be able to represent equivalent crystallographic directions.
equivalent, yeah. got
Equivalent crystallographic directions as a permutation of 3 symbols.
it. 3 symbols, yeah.
Whereas for cubic system, it is all permutations of 3 symbols will represent a family of equivalent directions. But
Got it, sir.
But the representation of a crystallographic direction should be possible in any crystal system.
Yeah, noted, sir.
Yeah. Any other question? Okay, if there are no further questions, let us stop here and then we'll meet next week. Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
You will be
Thank you,
uploading
sir.
the slides, right?
Thank you, sir.
Yeah.
Professor, you will be uploading the slides in the portal, right?
Yes, I'll do that. I'll most likely do it tonight. Yeah.
Sure, Professor. Yeah. Thank you.
Okay, bye.
Thank you, sir.
Thank you, Professor.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.